What's going on, Wrong channel.
A huge thanks to my Patreon supporters for making this episode possible. Good morning, fellow mathematicians. Welcome back to another video. Hot beverage powered Stirling engine. I love that little thing, putting it on my cup of coffee each and every morning. You can find it over at STEM merch, just like all the other merch that you can see here. So, as promised before, we are doing more physics on this video, and this episode marks the start of a mini-series, namely on introductory quantum mechanics. And today I would like to separate the Schrödinger equation with you, the time-dependent one, and also talk about the momentum operator a little bit and the Hamiltonian and quantum mechanical systems. But before we dive into the main video, I would like to give a huge freaking shout out to today's sponsor GAOMON, who were kind enough to provide the channel with yet another one of their absolutely fabulous pen displays. Last time around I got this one, PD1560, and it was already pretty amazing, but this one right here blows it out of the window. Seriously, this thing in terms of performance and how it looks and everything is just way too fucking cool, and you can find more information about the specs at the end of the video. But one more information, it's Black Friday week, and you can get both this one and also all the other pen displays over on Amazon for a really low price currently. At the moment you are going to receive the PD2200 for only $374 right now, so it's 15% off, and it's really great deal if you ask me. And also the PD1560, which I reviewed last time around, is at an all-time low. Never has it been this highly reduced. 34% off, coming at a price of $238, which is absolutely amazing if you ask me, and they really do their job. So if you're a fan of remote teaching, drawing, etc., Photoshop, you must get yourself one of those. They are absolutely freaking cool. Now that we are done with this introduction, I would like to get to the main meat of the video, namely taking a look at the time-dependent Schrödinger equation, separating it Andrew-Dodson style by using a tablet. Okay, stealing your content yet again, my boy. Okay, I'm terribly sorry, I'm a filthy guy. And after that, talking a bit about operators. Let us dive right in, shall we? So most quantum mechanics books, such as Griffith's, always start off with the probabilistic side of things, but I would like to start off where we ended up with on a Baking Maths episode that I posted like 2 years ago. Namely, it's called the time-dependent Schrödinger equation. It's called the time-dependent Schrödinger equation because this thing is dependent on the time t. Who would have thought? So to make things really short, basically what we are interested in is to separate this equation up here into something that is time dependent and the other one that is time independent. This time independent thing is called the time independent Schrödinger equation, and actually we can find out the time dependent solutions to this system right here kind of easily by basically superimposing the time dependent solutions with the time independent solutions. Okay, so this is something that we are going to take into consideration later in the game, but for now we would just like to take a look at just a separation ansatz that we are going to use on this partial differential equation. If you've never dealt with a partial differential equation before, this one right here is one that we can really easily separate into something that is way easier to handle. So just one or two more details about what we have in here in this equation actually going on. So it's kind of weird what we got here. We got this I, okay, that's just imaginary unit, okay, part of a partial differential equation, pretty surprising if you ask me. But also we have this h bar. This thing right here is the reduced Planck's constant, is something just 1, okay, if you deal with natural units. And then we have this capital psi. This thing is called the wave function of the system, and in quantum mechanics we are actually interested in seeing how wave functions behave under the influence of the Schrödinger equation right here in an energy dependent system, you could say. Since it's a wave function, it's dependent on the location and the time it takes to propagate over a certain amount of distance, you could say. Then we also have m as being the mass of a particle, for example, and last but not least we have a potential, which is as usual only dependent on the distance x, basically, just on the place in the system. And yeah, the potential is actually time independent, which comes in quite handy when separating this whole thing right here in the end. Now we are going to dive right in and use one of the methods that you should always use at first when trying to solve for a certain set of solutions of a partial differential equation. It's called the separation ansatz. So basically, there are a few things you could possibly do. At first you could assume that your wave function is 0. Trivially, it holds if you plug 0 into each and every wave function right here, deal with the derivatives, then, well, yeah, trivially, this partial differential equation is going to be satisfied. Then there could be just constant solutions. So this is one thing you could also take a look at. So that's the second thing most people take a look at first when dealing with partial differential equation. And last but not least, there's the separation ansatz. So for this, we are going to take a look at our time and also distance dependent wave function. And what we are going to do is we are going to say, okay, why not assume that we can write our capital psi as being the multiplication of, let's say we have small psi with respect to x, this right here is our distance x, times, and on the separation ansatz we are going to assume that it's basically something that we can track apart, okay, into multiplication of two one variable dependent things. And let's say eta is the other function which is with respect to t. We are going to assume that a set of solutions is going to exist to the Schrödinger equation satisfying this exact condition right here. Like mentioned before, we already said, okay, trivial solution is part of set of solution to each and every Schrödinger equation that we're having up here. So we are going to assume that our capital psi is not equal to 0. This is something that we are going to assume, and under the assumption that, for example, psi and also our eta, so small psi and eta, are complex variable functions, then we can assume that both of them are not equal to 0. Okay, since the complex complex numbers form a field, a product can only be 0 if one of the parts is 0. Okay, and so we can also assume that small psi of x is not equal to 0, as well as our eta of t. Both are non-zero, meaning we can safely divide both sides later by it, which is the point of this little argumentation right here. Now, we are just going to plug our new definition of capital psi up here in the time-dependent Schrödinger equation and see what we're actually going to get. So let me plug everything in here. Now that we are done with this, just one little thing that you must take into consideration. Partial differential equation, like we have up here, is a bunch of operators going on, real or complex operators. Thing with operators is, if we were to divide both sides, for example, by capital psi that we're having here, so by those two parts, you cannot, for example, cancel out the small psi of x right here, because we are actually taking the differential of the small psi of x. Please take this into consideration when dividing both sides by something. Don't just cancel stuff out. It's a bunch of operators going on here, so we need to be really careful with everything. So at first I would like to do a few more manipulations here, because actually, for example, our eta of t is independent of the differential with respect to x. So what we can do is we can bring it to the front, for example. Also we can bring our small psi of x to the front right here, leaving us overall with a partial differential equation which looks as follows. And now we can go ahead and divide both sides by what we have here exactly. So meaning, we are going to divide both sides by basically capital psi, leaving us with this part right here. Okay, we're also going to divide this part by it, and last but not least, this one right here. And like mentioned before, you can just cancel out, for example, those two etas. This doesn't work out because we are applying a real operator to this eta up here, so you can just do that. But what you can do is you can cancel out the small psi here, for example. Also, you can cancel out the eta on this part, and obviously this right here is going to die in hell too, leaving us overall with the following. Now the best thing about this equation that we are having here is the following now, and this is a very crucial observation. If we were to take a look at the dependence of the right hand side, for example, you might notice something. So we got rid of all the etas on this right hand side, meaning this part right here is dependent on x. Also, v of x is obviously dependent on x, meaning overall the superposition of those two is with respect to x overall. So the right hand side is basically a function with respect to x. What do we have on the left hand side? Well, obviously we got rid of all the small psi's right here, meaning all we have here is, well, a function which is with respect to t. And now we are setting two functions equal, which are dependent on different variables. Now what were to happen if we apply a small change in x to this whole equation right here? Okay, let's say both functions right here were equal to 3, for example. Okay, at first, just a numerical example. Now we apply a little change to x right here. Okay, we apply a little change to x, meaning it's going to be raised by 2, for example, giving us 5. But we applied an input to our x side. What happens to the side which only has t in there? I mean, there nothing really happens. I mean, nothing is going to happen. It's with respect to t. So we would end up with an inequality. Same argument here. We apply a small change in t, for example. Okay, then this is going to be raised to 5, but nothing happens with the x side. Okay, so both sides can get any real input, because then if they were dependent on x and t either way, then well, we would get an inequality, meaning the only real solution to this problem could be that both of the functions are actually constant. But since this right here is an equality, okay, on the one hand we have f of t is equal to some constant, on the other hand we have f of x being equal to some constant, but since f of x is equal to f of t, by the transitivity of this equals relation, we also know that both are equal to the constant c. Meaning we have two functions, okay, two sides, which are both equal to the same constant, which is a real plus if you ask me. And now we can even do better when it comes to the constant. If we just take a look at, for example, our right-hand side of the problem, we are going to have that we have something del x squared psi plus v of x. I mean, in physical systems, and this is equal to a constant, in physical systems we must have that the units are actually equal, okay, on both sides. Meaning the units of c must be equal to the units of the left-hand side that we're having here. Now, what are the units actually on this left-hand side? I mean, what are we having? There comes another thing in. We have the superposition of two things, okay? We are adding something to another something, and this one something is a potential. By definition, a potential is defined as being an energy quantity. So unit-wise, our V is having the same units as some energy E, for example. Now you can't add pears to apples, for example. So if our V of x are apples, and let's say this part right here are pears, then if you add those together, you are not going to have the same unit anymore. Those are apples and those are pears. Doesn't work out. So meaning this part right here must also have the units of an energy. Okay, so the units of this part are also the units of an energy. Overall, we are adding an energy to an energy, meaning the units of C must also be the units of an energy. And this right here is a statement that is actually true. The constant that we are having is, by definition of those units that we just superimpose on this whole problem right here, are actually the units of an energy. Meaning, for example, this side right here, okay, this right-hand side of the problem is actually some energy of a certain system. And this is our quantum mechanical system, which is actually time independent. And this right here is what we call the time independent Schrödinger equation. And let's write it out very quick. This thing is the time independent Schrödinger equation, TISE, okay? You can write it out like this. This is just a conventional thing. Many people use this. And we would like to manipulate this a tiny little bit further. Namely, I would like to multiply both sides by psi because it's not equal to 0, leaving us overall with e times psi being hence nothing but negative h squared over 2m times del x squared of our psi plus v of x times psi. This right here is the real final form of the time-independent Schrödinger equation, and it even takes another form. Namely, what we have here, this tiny little part right here, that's a real operator in some way, okay? So like the differential that we're having here, that's a real operator in some way. This is just a derivative, the partial derivative. And also we are having this part right here. And what we can basically do is we can factor out our psi that we're having on both terms. It's not really called factored out because we are basically applying a real operator to our psi. You could rather say it's like anti-applying or like not applying our operator anymore to psi or later applying it to it. But to make things a little bit more clear, let's just say, or let's just act like this is a certain number, and on numbers you can factor out common factors, leaving us overall with e times psi being equal to, okay, and what we have in parentheses is now negative h bar squared over 2m times del x squared. Does look weird if you have any if you haven't anything next to the differential operator, but you might want to get used to that because this is just a user convention used in quantum mechanics all the time and many other branches in mathematics, times psi. And now our system is going to take a certain form. Namely, we are going to have a certain operator here being applied to our psi, and this is equal to E times psi, okay? And this operator is called the Hamiltonian, and if we deal with an operator, we are going to put a tiny little head on this whole thing. Meaning overall, our Schrödinger equation, our time-independent one, can be rewritten as E times psi being equal to H bar times psi. Not H bar, the Hamiltonian times psi. I'm terribly sorry about that. And this right here is the main problem in quantum mechanics, okay, introductory quantum mechanics. We want to solve our eigenvalue equation. This is what this thing is called for certain wave functions psi and for certain potentials v of x. You can, for example, say v of x is equal to 0, then you have a free particle, and then you need to find out what the solutions to this eigenvalue equation actually are. And now we are basically done with the main part of the video. We have separated the Schrödinger equation, but I would like to take a look at the Hamiltonian for a second more and the so-called momentum operator. Namely, the Hamiltonian is something that you probably encountered already before on classical mechanical systems. Namely, in the normal case, we have that our energy of a system E is nothing but T plus V, meaning this is the kinetic energy plus our potential energy, meaning it's going to be of the form m over 2 times V squared plus our capital V, okay, just our potential. Now there's also something completely different that we can take a look at, namely, many of you might know that the momentum of a system is being defined as mass times our velocity. And actually, there are a few similarities in here, if you take a look at that. So on the one hand, we have m times v squared. This is kind of the form as p squared, okay? Just our momentum squared. Just with the one difference that on this side an m is missing, and yeah, here on this side we have one m too much. So what we can do is we can divide both sides by m, leaving us overall with what we desire. This part that we are having up here in our equation is nothing but, well, basically p squared over m, meaning the total energy of a system can be redefined as being nothing but the momentum squared over 2m plus our potential energy. And this is actually kind of what we have here of this form right here. And actually, many mathematicians and also physicists define the conservation of energy law basically being as a Hamiltonian. Hamiltonian has the property that we are dealing basically with canonical whatsoever, momentum, momenta, okay? And yeah, total energy of a system can be defined as being the Hamiltonian. Same thing we have up here. And now we can basically see some analogies here. I mean, our potential V is still the same, but our kinetic energy part that we have up here in this conservation of energy basically in the Hamiltonian is looking kind of different, and we need to make some manipulations to find out what our momentum actually is in a quantum mechanical system. And it's actually rather easy to find out what our momentum actually needs to be by just equating our kinetic energy parts basically. So what we have is we have negative h squared over 2m, and don't forget your real operator del x squared must be equal to p squared over 2m. Now you might notice that under the condition that the mass is not equal to 0, it's going to cancel out. Now we are going to be left with p squared being hence nothing but negative h bar squared del x squared. Now what we have is something of the form something squared is equal to something other squared. It might not seem like this right-hand side is totally squared by now, but remember which quantity squared is going to give us our -1, well, I squared. Meaning we can rewrite this as being p squared, being hence nothing but, okay, we're going to have I squared times h bar squared times del x squared. And if we have a quantity squared, okay, multiplication of things squared, we can just factor out the squared. And you must interpret this squared as not being a real power of something, an exponent, rather interpret it as a real operator being applied to a quantity twice, because we are applying the differential at first and then a second time. And now we can take the square root on both sides, leaving us basically with P being hence nothing but plus minus I times h bar times del x. Okay, now we have two branches, the negative and the positive branch of this momentum operator. Which one should we choose to be our real momentum operator? I wouldn't call it really convention. We are going to choose the negative branch. It more has to do with the relativistic side of physics. Let us take a look at the other equation that we still have going on up here, because we also know that the left-hand side is equal to the same constant c, which was our energy of the system. I've written out the other operator equation, and the only thing we need to do right now with this one is multiply both sides by eta, okay? Leaving us overall with another operator equation, basically, just like with the one that we are having up here. Remember, we can basically apply this operator to our small psi, leaving us also with an equation being of the form E times psi being equal to momentum operator times psi in some way. So if we just multiply both sides by eta, we are going to get I h bar times del t, okay? Let me factor it out real quick. Times eta, okay, not factoring it out, anti-applying it, you could say, is equal to E times our eta. And now once again we have this operator equation, namely we can define ourselves a so-called energy operator. It's just like the Hamiltonian or our momentum operator. Also for the momentum operator we like to put a little head on top of it yet again. We have that I h bar times del t is nothing but our energy operator. For some reason on the energy operator you don't pop a head up there. I don't know why that is, but most physicists don't do that. It's quite confusing, but they don't do that for some odd reason. And now, what can we find out about the sign of this operator? Well, the sign of this energy operator is positive. With this reason and relativistic reasons in physics, we like to define ourselves the momentum operator as being negative. It's basically the negative position counterpart to our time-dependent counterpart that we're having here. Meaning we also have the momentum operator being defined as negative I h bar del x. Those are two extremely important operators. And actually, this equation that we have up here can be easily solved. This is just an exponential function that you can ridiculously easy solve. Namely, what you are going to say is that we are going to have eta prime divided by eta, hence nothing but E divided by I times h bar. And now you can find out what the solution to this differential equation is. This is just an exponential function of sorts. It's really extremely easy to find this out, okay? Maybe we are going to deal with this in another episode. But yeah, with this solution to this differential equation multiplied with the solutions to the time-dependent Schrödinger equation, you can actually find the solutions to our first equation that we're having up here, namely the time-dependent one. Those are two really stupid words. And this right here concludes the first episode of Introductory Quantum Mechanics. Namely, what we wanted to do is we want to separate the Schrödinger equation and talk a tiny little bit about our operators that we're having here. But before we end the video, I would like to talk a tiny little bit about this beautiful piece of tech. It's really something that I highly appreciate. I can't believe that they sent this thing to me next to the first one they sent to me, and it's really godsend if you ask me. And like mentioned before, you're going to get all the GAOMON tablets nicely reduced over the whole week, over the whole Black Friday week, over on Amazon. Check it out. All the links will be down there in the description in some way. I don't want to talk too much about the specs right here because they are actually kinda similar to the ones that we're having here. So as for the pen, let me talk about the things that came with the new GAOMON tablet actually. So once again, the GAOMON tablet came with itself, with the GAOMON tablet. Also with a pen. This pen once again has those very huge levels of pressure that you can apply to it. I think it was 8,192 levels of pressure that you can apply to it. And maybe you have seen it while riding, that sometimes if I press too much on it, it's really hard to get a hang of it at first. Okay, it's really sensitive. You are going to see that you are going to get some very nice strokes. So from very thin to thick strokes, you can get everything. way many more levels of pressure that you would ever need levels of sensitivity. Other than that, the display of this thing is huge. If we were to compare those two pen displays, let me just give you an idea. Those are the two compared, okay? So my first GAOMON tablet fits onto the writing part on here completely, okay? It's way more huge. The pen display has a 21.5 inch diagonal, which is extremely huge. It's like a small TV, you could already say. I could put this into my bedroom as a substitute TV too. And yeah, overall, it just looks absolutely fancy. It has a lot of buttons here on the side. Other than that, you can put macros on all those buttons. The overlay with the software that you need to install on your PC works the same as with the other GAOMON products. So it's very similar. You can set shortcuts here, you can zoom in, move your Windows Ink workspace around, etc. You can use it for remote teaching, you can use it for Photoshop purposes, drawing, everything, animation. It's just absolutely fabulous. As per usual, the pen also came with this pen stand and with substitute little pen stickies. Okay, the things you put to the front of the pen, right here. And actually this pen is even more huge than the other one before. It's rechargeable, if I'm not mistaken. Even though I didn't have to charge it yet, but you have this really nice soft grip going on here, and it's way more comfortable than the other one. This is what I highly appreciate. And yeah, other than that, the performance of this thing is just overall great, and I'm using it all the time by now. If I do notes, if I scribble a bit, if I do remote teaching, if I do tutorials here, all the time. I can't live without this thing anymore. I'm being serious about this. It made my life so much easier. It does outdo, for example, my Surface Pro when it comes to drawing, etc., or taking notes. Only one little downside is, so with this GAOMON tablet, we already had the little downside that you had to screw and unscrew the stand all the time to take it with you. So there was a stand that came with it, and you can screw it to there. Also, there was a tiny little bag that you can use to take it with you. This was the bag right here. I'm taking it with me from time to time to school. And well, you can just put it into here and take it with you. So the downside here was already that you couldn't put the stand into here, so you were basically forced to take the stand with you in a separate case, for example. Now with the new GAOMON tablet, we have the issue that the stand is already screwed to this whole thing. So you can't really unscrew it. Also has to do with the reason that the cables are actually way better on this one right here. So the cables are hidden behind the tablet. This was a huge downside for me with the other tablet because the cables came out from the side. But this one right here has very nice cable managing come with it. But yeah, you can unscrew it, meaning you can't really take it with you. It's extremely hard to take with you. And I suppose this tablet is really not one that you should take with you too often, or overall you shouldn't take it with you because it's so huge you can't really fit it into your backpack, for example. So I couldn't fit it into my rich backpack even if I wanted to. It just doesn't work out. This thing is bigger than my rich backpack overall. So yeah, just keep this in mind. Cable managing is way better, but you can't really take it with you. It's just way too big. And this basically concludes my tiny little review next to the episode on quantum mechanics. If you want to try out the GAOMON tablet, make sure to check out the links at the top of the description. I'm not going to receive any money from you buying over there. Everything I received was this tablet right here as well as the other one, and I'm totally satisfied with this. I don't need money for this service. This is more than enough. This thing is brilliant. I love it. You should definitely check it out. I thank you guys for watching. If you enjoyed this video, then please like, subscribe, and comment channel if you like. If you want to support channel a bit more, buy this teacher like Grace, support channel on Patreon. Now in the next video, wish you guys a flammable day. Ciao!